Welcome all. Welcome everyone. Very warm greetings from Mercy Technologies. So let's see our agenda. I think we did get a good foundation on trees data structure, and then we started the coding in trees data structure. So we saw that we can do or we can achieve the code using recursive approach in a concise way. And what we did is we started with our coding in the traversals, right? In order traversal, pre-order traversal, post-order traversal, etc. So we'll be continuing on the code that we are going to write. Okay, so I think I've given you homework on two questions, which is number of elements in a binary tree and finding the maximum element in a binary tree, right? So along with that, we maybe you could have tried even more or maybe explored a bit more, but keeping everything aside, let's continue the class, right? So we'll be doing the following programs in our class for today. So it's like finding the number of elements in a binary tree, finding the maximum element in a binary tree. Okay, finding the maximum element in a binary tree, finding the number of leaf nodes, searching for an element in a binary tree, and then introduction to binary search tree. So this is our agenda for today, and let's try solving one by one. Okay. So what would be our approach? Our approach could be like taking examples, right? I think we've been following this approach since quite long. So let's straight away go and try to see. Here in today's class, I'll be taking some example like this. Okay, this is a binary tree. Okay, this is a binary tree, and the following is example. So it has one. So it is a binary tree. It is a binary tree. Okay, fine. So it's like starts with one, right? It has two children. The node either has one, two, or 1, 0, 1, or two children. So that's why this becomes a binary tree. Let me write this same binary tree in my Microsoft whiteboard as well. So what is that? 1, 2, 3, 4, 5, right? So this is our binary tree. 1, 2, 3, 4, 5, right? Right. So let me go back. So previously we have done the questions in HackerRank only. I find a few questions are not properly given in HackerRank. So it's like we just need to test it using our main method. So what I did is like we have done this question, right? So what is that? Finding the height of a binary tree. Okay. So finding the height of a binary tree, this question we have already discussed previously. This question we have discussed previously already. So what I did is I've taken a main method. Okay. Here's a main method. So inside this main method, I've created a node with root. And I'm saying root dot left is 2, root dot right is 3. The same thing, right? Root dot left is 2, root dot right is 3. And root dot left is 4, root dot left. Okay. So root dot right, root dot. Okay. Here I think I've done something like this. Root dot left and root dot left dot right is 4 and 5. So this is the representation, or is the representation of our main method. Okay, so using this, what would be our height? So the height would be 2, right? The height would be 2, right? So this is how it is. Let's try to see if we are getting. So what we did as part of height, so we did, if root is equal to null, then you return 0, there is no height. Or else what we are doing, my root doesn't know what is its height. It asks its left subtree, and then and again it asks its right subtree, and finally it gives me the height, right? One second. So finally it gives me the height. uh, Return right height plus 1. So yeah, let me try to run this program for you. So what is my proceed, right? So this is my height. So I think after we have done this, we have to do this one, right? Return is greater than, yeah. So this is what we have done, guys. This is what we have done, guys, in our previous example. So with this we concluded our class. Now let's move for the next question. So what is our next question? Find the nodes count, right? Find the nodes count. So you just need to find what is the count of the nodes, right? I don't know if you have done this question, or if you have your pen and paper with you, you can start writing this as well. So in the meanwhile, even I also will be writing this question. Okay, I also will be solving this question. Okay, so let's see. So let's say what should I do? I should find the number of nodes, right? Number of nodes, right? So this is my example. So this is my example. It says 1, 2, 3, 4, 5. So the number of nodes should become 5, right? So what I can say is if, let me try to write the base condition. If, so what it says, root equal to null. So what is my condition in this case? Return 0, right? There shouldn't be any number, right? There shouldn't be any number. So in that case, so again, now I don't know, root doesn't know what is its count. So what it says, maybe I'll say int left count. So left count is equal to, what I say, get nodes count of root dot left, right? So then I say int right count is equal to get, and then I say root dot right, correct? So then what I should say, I should count left and right, return left count plus right count plus 1. Because the left count, I'm a root, I'm asking what is my left count to my left subtree, I'm asking what is my right count to my right subtree, and I'm counting myself also, like I'm counting what is the root. So the root is also having 1, right? That is also I'm adding over here, and finally I'm returning those count, and finally this should give me the count. Let me try to run this program for you and make you understand what exactly it is, right? So what it says, the count is 5, right? This is what the count is. The count is 5, guys, right? So this is the same example. The previously we have done some height. So here only the condition changes. Whatever is my left count, I'm taking. Whatever is my right count, I'm taking. So finally I'm returning left count and right count. And what am I doing? I'm trying to add 1 to it, and finally getting the number of nodes in my tree, right? This is how we calculate the number of nodes, guys. Are you able to understand this code? So let's see, like what would be the pre-order for the tree that we have taken. So we can do something like this, right? I want you guys to answer first. 1, 2, 4, 5, 3. Yeah, that's correct. So something like this, right? I want a pre-order. Maybe I'll put some dashes over here, something like this. This is shortcut that we have learned. Okay. So what I'll do is I'll start, and I'll be starting as close as possible to my tree. I'll be drawing one line. Okay. So wherever is the intersection point, so that gives me the pre-order, right? What I understand over here is, let's say the thing that I want, that I understand over here is 1, 2, 3, 1, 2, 3, 4, 5. So I'm going to every node, right? Maybe I can have a variable called count. So before printing, what I can do is I can do count plus plus. Okay, I can do count plus plus. When I can do count plus plus, finally after I'm done with the final node, I can print count, right? So this is also one way. This is also one way of trying to find out the count. The same thing what we did is, like, I mean, we followed our approach is the same thing in pre-order. We can have some variable called count, and finally we can say count plus plus, etc., etc. But we have followed this approach, the approach of root saying, okay, if I'm null, then you return 0. If not, then what I say is left count. I take the left count, then take the right count, then calculate the left count and right count. And what am I doing? I'm adding 1 because I want to add myself also. So that is adding root also to my actual count. Okay, so let's move to the next question. Okay, let's move to the next question. So what is the next question? Get maximum element, right? Get maximum element. You can follow a similar approach, guys. Start writing. In the meanwhile, even I also will start writing. Okay, in the meanwhile, I also will start writing. You can I think you have a pen and paper with you, so you can start writing the code with this one. So before writing any code, as I told you, the base condition is the heart of every recursive program, right? Base condition. So this is the base condition. Okay. So what could be the base condition for this? What could be the base condition for this? Something like this. Okay. Get maximum element. Get maximum element. Right. For example, let's say we are taking this example: 1, 2, 3, 4, 5, and 3 here. The maximum element will become 5, right? Maximum element will become 5. Okay. So let's say I'm trying to write something like this. Root is equal to null, then what I say is return 0. Okay, so I'm trying to write return 0. You also can continue writing, guys. I also will be writing here. Okay, so if root is equal to null, then return 0. If not, what I'll say is I'll ask my left subtree what is my max, and I'll ask my right subtree what is my max, and I'll try to give the max out of it, right? So what should I say is int, or I can say left max. Okay, left max is get, then I can say root dot left, something like this. I can say int right max is equal to get maximum element of root dot right, root dot right, and I'm saying I should give the maximum out of it, right? Return dot max of, so return dot max of, I can say root comma dot max of left max, right max. I can do something like this, root dot right. This is how we can write, this is how we can write the code for getting the maximum element, guys. The code for getting the maximum element. So you can concentrate on here. So what we did in the base condition, we checked if root is equal to null. If root is equal to null is, which means we do not have anything, so which means the maximum element we are returning to be 0. Okay, so if not, then what is root asking? Root is asking its left subtree, hey, give me your maximum element. So recursively I'm calling, saying root dot left. So I'm saying again right max is equal to get maximum element root dot right. Okay, so here what am I trying to return is I'm trying to get the maximum out of left max, right max, and left max, right max, and my root itself, right? So this is how it is, guys. Math.max, there is a method math.max. So it can only take 2 arguments, right? One is int a and int b. So fine, we are doing that. We are trying to find out the maximum out of left and right, and finally again we are trying to find the max by comparing root with these two, and finally we are returning the same thing. Okay, we are returning the same thing. I say run as, and finally, just a second. Oh, so this is my tree. I'm saying 1 2 3 4 5. I've taken that. Finally, I'm trying to run it again. Okay, so when I say it is giving me the maximum element as 5, right? It is giving me the maximum element as 5. So this is how we can write the code, guys. Okay, this is how our sample code looks like. So let me try to ask. Okay, so what I want to say over here is, like, we have taken something like this get max. Okay, so we are trying to do something like this. Root is equal to null. We are returning 0. We are trying to calculate the left max and right max. Fine. So what we told is, like, our example works fine with a positive number, but when we try to do that with a negative number, it gives us 0, right? So which means it is not working with our negative number. So that's why what I want to say is, never make assumptions, right? Never make assumptions. Instead of making assumptions, if you have doubt something like this, or if you actually have doubt something like this, then you should actually ask the interviewer that, what is my expected input? What is my expected input? Is it negative numbers? Is it positive numbers, or how is it? What is the range? Okay, so here if you observe, we don't even know that we have made an assumption also. That is one more biggest problem, right? So it's like we just start coding by taking some example and try to dry run, and if it works, we straight away show it to interviewer. The thing is, like, we need to ask as many questions as possible, especially while working with numbers. You should be utmost cautious, right? So the questions that may go wrong, is, it's not questions that may go wrong while working with numbers. These are the three important points, guys. Like, are negative numbers present? So this is one question that you need to ask. What if zero occurs, then what you do? This is one more thing, right? And then range of numbers. This is something that you need to be cautious, right? So you should always post a question saying that, are negative numbers present? If zero is present, what is the range of numbers? Right. One question that I want to highlight over here, if it's a HackerRank assignment, yes, we can do it, because in the HackerRank they give it. But questions, like this kind of questions, like people, or they ask you to just test your knowledge on trees, and finally they'll say, no, the code that you have written is false. The reason is it's breaking in this kind of in this places. So that's why you should not give give chance to the interviewer that, even though you know the concept, like, you shouldn't fail in this kind of steps, right? In this kind of steps, there'll be some boundary conditions, like, what if there is a null kind of, what if there is something else? So which means, for any recursive program that you write, the first thing that the people observe is your return condition, right? Your return condition, if your return condition is proper or not, right? Let's try to do, or maybe I'll try to run the example over here. So what is this example saying? So I told you that there is minus, right? There is minus. Let's say I showed you by having minus numbers. Let me try to run this for you. So this should actually be -1 with the maximum element, but my output will be giving me 0, right? Oh, sorry. Okay. Wrong thing. So the output should be giving me 0, right? So this is how it is, guys. So instead of getting 0, you should be getting as -1. But since this condition is wrong, so then we have to modify this condition. So how should you modify this condition, guys? Can you write -100, or maybe -1000, or -10,000 or something? So it's not like that. You should be giving -infinity, right? Something like this. I'll show that to you. Yeah. So your return condition should be something like this. It's not a return 0, right? It's not written 0, but it should be return minus infinity. Okay, it should be written minus infinity. But how do you get that in our programming language? For example, in Java, how do you represent that? So it's something like this. It's like integer, so integer dot min value. Okay, so what is the integer dot min value? This is the minus infinity. You can just check what is this integer dot min value. It has some representation, something like this, but you really do not need to care about what exactly is the implementation. But here you are actually returning your infinity. Now let me try to run this program. It should be giving me -1 as my output, right? So this, it is giving me -1 as my output because I have modified my return condition. That's it, right? So guys, are you able to understand? To our next example, right? So we need to calculate the number of leaf nodes, guys. Number of leaf nodes. So I told you in our example, okay, in our example, maybe I'll try to write it once more. Okay, so what is our example saying? Our example is saying something like this. So it is 1, 2, 3, 4, and 5. Or maybe I can say something like this: 4 and 5. Okay. Okay, so how many leaf nodes are over here? How many leaf nodes are there? Leaf nodes are nothing but the nodes without children, right? Without children, this is a leaf node, this is a leaf node, this is a leaf node, right? So these are the three leaf nodes. Let's see. One second. One second, please. Yeah, so there are three leaf nodes over here, right? There are three leaf nodes. Okay, so we are clear with the leaf nodes and its understanding. So same thing, let me try to write code for it here, and then we can implement that. Okay, so what it says, I can say something like this: int get leaf nodes. Okay, so something like this: node root. So my condition would be if root equal to null, then return. How many leaves would be there if root is null, guys? Then 0, right? So it will be 0, right? Right. Now I'll say int left leaves is equal to get leaf nodes of root dot left. Okay, root dot left. I can say int right is equal to get leaf nodes of root dot right. So I have two things. So now I should return, right? I should return. So what should I return, guys? It should be left leaves plus right leaves. Okay, left leaves plus right leaves. So again there is one more thing. Okay, again there is one more thing. Again there is one more thing. So what is that? What is that? We should count the left leaves and then we should count the right leaves, right? Return left leaves plus right leaves. That's it. We need to count both and then we need to return, right? And then we need to return. The reason is, like, for example, let's say in our case, when there is something here, then you are not returning anything, you're returning 0. And now you are counting and you're counting left leaves and right leaves, left leaves and right leaves. For example, left leaves and right leaves. For example, let's say my input is something like this, 2 and 3. Okay, what am I trying to do? This is not null. Then I'm coming here, it is returning me 0 0. Okay, fine. And now again I'm checking. So what is my count? And finally I'm returning the same thing. Let me show that to you guys. Let me show my code to you. So what is my what is my code saying? Let's say I try to write this. If I say root is equal to null, so what should I return? Return 0. Fine. This is how we need to get. I'll say int left leaves is equal to, I'll say get root dot left, correct? So now I'm saying, oh, sorry, now I'm saying int right leaves is equal to get number of leaves root dot right, and finally I'm returning left leaves plus right leaves. That's it. So here maybe I'll try to run this program and show you what exactly is my output. So I'll try to run this program and say, oh, it's giving me what? It's giving me 0 as its value. All right, 0 as its value. The reason, if you see it, guys, the reason if you see it, the reason if you see it, our condition, our written condition is something which we have not written correctly. So our written condition is not written correctly. So what is our written condition, guys? Root is equal to null. Okay, I'm returning 0. That's fine. Now again I should say root dot left is null and root dot right is null, which means it is having a leaf, right? This is my if conditions. What is my if condition saying? If condition is saying something like this: root dot left is equal to null and root dot right is equal to null. So which means my root is not having left child and right child. So what would be the case over here? Return 1, right? So this is my one more base condition, right? This is my one more base condition. So what should I say? If it is left out in this way, then I'm returning 1. Now let me try to run this program for you. Okay, now if I run this program, it says 3 is my answer, right? If you see our example, 3 is our answer, right? 3 is our answer because the number of leaf nodes are 3. Same thing, guys. This is how you need to write the code. First maybe you try to write with similar base condition, you try to do the same example over here, but you finally find that since it is coming 0, your condition itself is wrong. So maybe I need to add something to my base condition. So what is my base condition? Base condition is if root dot left is equal to null and root dot right is equal to null, finally I'm returning 1. The reason is if the root or if the corresponding node does not have a left child and does not have a right child, then I can count that as 1, right? Then I can count that as 1. And finally, this is how in my written condition, those numbers get added up. And finally, I will be getting my output something like this, right? My output something like this. So I'll be getting 3 as my output, right? 3 as my output. Guys, you're able to understand this code. So we are able to run it and we are able to take the small example. Let's say we have taken a main method and finally we are able to achieve just by tweaking our base condition. Now guys, since you have a pen and paper with you, start coding for this one, right? You need to search, right? There is one more which is search. For example, in my case, this is the example, right? I need to search for an element called 5, right? So which means my search method is expecting the root node and it is having some data called x, right? It is having some data called x. Like for example, let's say if I pass 5, then it should return me this corresponding root, or else it should return me some null, let's say. Okay, it should return me null. This is the sample input. So now we need to actually implement this code, guys. Okay, we need to actually implement this code. Now I will start writing. In the meanwhile, you also start writing. Okay, so let's say if root is equal to null, same pattern we are following. Root is equal to null, So when you are trying to say root is equal to null, what should you do is return null. Okay, so you should return null. So now what am I trying to do is node left search is equal to, so I'm saying search of root and x. So what is this root? It is left search, right? So that's why I'm saying root dot left. Okay, that's why I'm saying root dot left. Now I'm saying a right search node. So I'm saying right search is equal to search of root dot right, and then I'm trying to do something like this. Okay, now after doing this, if left search, that means if it is not coming to this if condition, then left search should be having something, right? So which means what I can say is if left search is not equal to null. So if left search is not equal to null, then what should I do is I'll say return left search, right? Again the same thing. If right search maybe I have written the wrong name here, RIGHT. Okay, if a right search is not equal to null, so what am I trying to do? I'm trying to return a right search, right? I'm trying to return right search. Until here it's well and fine for me. So after these cases are also not coming, then what can I do is I can say return null. Okay, so this is our simple code, guys. This is a simple code. What we try to do is we are trying to first we are seeing if it is existing in the root or not. If not, we are returning null. So then my root is not knowing how to know or how to search, right? How to search. So what should say? Root will ask its left subtree, hey left subtree, you search my element in your left part, right? And my right will say you search for its element in your right part. And let's say you are getting something in left subtree, and let's say if it is not null, then you're returning it. Again, in the right subtree, if you're not getting it, then you're returning that. And finally you are returning null, right? Finally you are returning null. This is our simple code just to actually find what exactly we are trying to do, right? So what am I trying to do? I'm trying to search for an element called 5, let's say. Okay, so I'm trying to search for an element called 5. Okay, trying to search for an element called 5. Let me search that. Okay, what it says, null pointer exception. What is the null pointer exception? Let me check. Search for an element. So where it says 5, search root comma 5. There is this, right? Search of root. So what is my root? It is saying 5 dot data. So why is this not working? Or maybe I'll search for 1. Let's see. I don't know if we have written a code which is wrong. Let's try to correct that. Okay, again it says null pointer exception. I think we are not returning correctly. Search root dot left, root dot right. Okay, so we have done something like this. Let me try to see my backup code. Are we doing something else? We have not written our one more condition, right? If root dot data is equal to x. I don't know, I missed this case. Okay, so if we need to write one more something like this, if this is the case, then you have to return root. Okay, so this is our program. So what it says, so first you are checking this is your if condition, this is a base condition. What it says, you are trying to fetch if root is null, then you are returning null. Now if root is equal to data, right, what is your root? Root is something that, for example, let's say I'm trying to search for one. I'm trying to search for one. I'm trying to see again root dot data, which means one is equal to the input that I'm passing, which is one, then I should be returning that root. Okay, let me try to run this again. So again, yeah, now it says I'm able to do. Okay, now it says that I'm able to write it properly, right? Let me show that to you guys. Okay, guys, are you till now? Right, are you able to understand this program till now? What we try to do is we had two first base condition, and after that we try to have one more base condition. We are trying to find the equality. If not, we are having left search and right search. If left search is not equal to null, then you are returning left search. If your right search is not equal to null, then you are returning right search. The same thing, the same example, but we have tweaked a little bit more to search, right? We have tweaked a little bit more to search. Guys, are you able to follow what I did? What I did as part of this code? Okay, cool. If you observe, there's nothing over here. We are following the same pattern, right? Since I ran and I got a null pointer exception, then I came to know, oh no, I think I missed something. I missed that. I missed some condition. I didn't want to waste my time, so that's why I just looked into my backed up code. Then I came to know that I have not written one more base condition. So this is what, when we call search method dot yeah, okay, when we call the search method dot data is required. See, my question is okay, fine, I understand. So what is our input, guys? Input something like this, right? Input is something like this, right? So let's say I'm not doing this also. Okay, I'm not doing this is not required. My actual intention is to print the data. Let's say I'm not doing it. So what am I trying to do is, when I try to run the Java application, so I need to override my what you call, I need to do a toString to my node, right? I'm directly printing its object value, right? So I need to override the toString. For example, let's say I can do something like this. What is that? Where is my node? My node is over here. I can say that here I should override the toString. So let's say I'm trying to do it. Source toString, and let's say I do not want to have the left and right. I just want to have data, right? I'm saying I generate it, right? So I'm trying to generate this one. Now when I have something like this, now I'm trying to run my example. Let's say instead of getting the object value, I'll be getting some readable value, right? Root.data, right? Data is equal to 1. Now let's say I'm searching it for 5, right? I'm searching it for 5. What it says, run as data is equal to 5. Only thing is, like, I didn't want to print the object directly, so that's why I was having on top of this, I'm saying dot data, right? When I say dot data, it directly gives me data, right? This is how it is. So it directly gives me data. That's what I did, Rishikesh. Just if you want to want to print it as part of data, then you just need to override your toString method. Okay, okay, cool. So this is how we can write the code for searching is. So if you see, we have done various examples, right? Height of a binary tree, number of elements, maximum element, right? Number of leaf nodes, searching for an element. Every program that we have written follows the similar pattern, right? Follows a similar pattern. Now let's try to find out what is the time and space complexity for this. Okay, time and space complexity for this. Now I'm trying to say, let me analyze for number of nodes in a binary tree. So number of nodes in a binary tree. So what happens? We need to go to every node, right? We need to go to every node. We need to go to every node. And finally, we have to get this left count. We have to get this right count. And finally, we are returning, right? Which means our time complexity will become, order of n. So what would be our space complexity? If you observe, while you try to calculate for the space complexity, I told you that there will be a stack which gets created internally, and finally there will be a stack which gets created. So something like this. So time complexity, since I need to go to each and every node, and that too for only one time, it is my order of n time complexity. My space complexity is order of, I can say, a question mark, let's say, for now. So let's say this is how I calculate my space complexity. So first what happens, maybe I'll call the function with f of 1, right? Now I'll call with f of 2. Now there will be a null, so which means the f of 2 will be going. Now f of 1 again calls f of 3, right? F of 3, right? F of 3. So what is f of 3 doing? F of 3 is calling f of 4. Okay. So f of 4, now there is a null, so f of 4 is done. So which means again it comes to f of 3, and finally f of 3 calls f of 5, right? F of 5. So which means again f of 5 is done, f of 3 is done, f of 1 is done, which means the maximum height of the stack is what? 3. But the number of elements that you have is 1 2 3 4 5. But the height of the stack that grows is what? It is only 3. What I actually want to say is there is the height of this tree, right? There is this height of this tree, right? The height of the tree is something called 3. So which means the height of the tree is the maximum stack length that can actually happen. So that's why the space complexity will be something like this. It is order of h, right? Order of h. But h is not a proper denotion for us, right? Not a proper denotion. So now let's say I'm trying to do something like this. Maybe I have some tree, something like this: 1 2 3 and 4, right? So my height of the tree is 4, and my number of elements are also equal to 4. So if there is an example of a tree which grows in only in one direction, something like this, 1 2 3 4, and finally that thing, not like this. Here, even though there are 5 elements, the height is 3. But here, let's say there are 5 elements, something like this, the height is 5, which means the space complexity is order of h. I mean, in theory, but I mean, like this is how it is in practical. But in theory, there can be examples something like this. So again, it can be order of n only, So which means this is what it is. The time and space complexity for our first program is order of n, and space complexity is order of n only. But in practical, after what we saw, it is order of h. Okay, order of h, and h can be n in the worst case. The height of the tree can be number of nodes in the worst case. That's what we have seen. So now let's go back and see the maximum element also. The same thing happens over here. We have to go to every node, and finally we are returning something. That's fine. But here what we have to do is we are trying to go to every node and trying to find out or do some calculation on it. So which means what I can conclude is the time complexity is order of n, and space complexity, what about space complexity? Space complexity is order of h again. Okay, so now the same thing happens over here also. Again, it is order of n time complexity, and space complexity is order of h, because we followed the same programming pattern. Okay, so now there is this element also. Again, it says the space complexity is order of h, and time complexity is order of n. The reason is, like, we followed the same programming pattern. Okay, so we followed the same programming pattern. People, if you get confused on how are we calculating the space and time complexity, I recommend you to watch the previous videos. I think we have done so many examples on space complexity, time complexity. How do we calculate that for recursive? How do we calculate that for iterative? Here we are doing with a recursive programming approach. I think even in our previous to previous class also, like, I just revised the theory for that. But in case you still get confusion, then maybe go back to the previous classes and try to find out why we are getting this order of n time complexity. Okay, so here one thing that I want to say is, guys, like, there is this search function. So we have written code something like this. Okay, we have written code something like this, but there is a way of improvising this code. There is a way of improvising this code. So what is that improvising is, like, let's say I find my element in my left search. I already found my element in my left search. Okay, this is searching for an element, guys. So a small bit of improvisation for this one is, let's say I already found my element in my left search. Then instead of going and doing right search, you do something like this, right? Instead of writing your if condition here, try to write your if condition over here. Okay, you try to write your if condition over here. So in case you already found out in your left search, then you're returning straight away from here. So instead of doing that again for your right search, right? Instead of doing again that for your right search, since you already found it in the left search, you're trying to return it, right? Even though in theory it doesn't improve my time and space complexity, but practically if we see an example something like this. So what I want to say is I'm trying to search for an element called 2. Okay, element called 2. So in here, in my left search, I could have already found 2, right? I could have already found 2. And if my left search is not equal to null, no, in our case it's not equal to null, so I can return straight away, right? Instead of again going and trying to search for right also. Okay, trying to search for right also. So as I told you, this is just an improvisation, just thinking practically, but in theory again still the time and space complexity will become order of n and order of n respectively. Let me try to run this program after we tweaked it. Let's see if we get it in a proper way or not. Yes, we are getting it, and we are getting 5. Let's say I try to search for 2, right? I search for 2. Maybe I'm trying to search for 2. It should be getting 2. Okay, so which means here it is returning from here. You can debug and see, guys. So in our left search, it will not even come to this part, right? Which means you are almost ignoring this many computations, right? This many computations. But as I told you, in theory it doesn't improve, but in practical, after seeing or taking examples, it actually is a big improvement, right? This is how it is, guys. So we have done, I mean, at least 1 2 3 4 5 6, almost nearly six programs in our today's class, guys. And let me tell you, all or maybe 80 to 90 percentage of the trees programs are or will be in the similar fashion, right? First, you try to you try to find out the base case, then try to find out all your base cases, then maybe ask your left child to do that, and then maybe ask the right child to do that. And after you get the results from left and right child, then maybe you try to have something like this. Here in our number of nodes, what we did is we counted, right? And our maximum element, what we did math.max. In our number of leaf nodes, again we counted, right? In our search element, again we did something like this. Okay, the thing is, like, it can be broken down into 3 parts, guys. First thing is, like, we have to get the base condition, and then we have to get the left subtree and right subtree computations, and finally again it's our conditions. How do we compute and return it back? It's so simple. We can break down that into 3 parts and we can start writing. So any complex problem that you take, right, try to write the base conditions first, and then try to do your left and right subtree computations, and then again after getting those data, you try to manipulate your data or try to make your data as per your requirement, and you return it, and your program will work like a charm. That's it, guys. So this is how simple we can work with tree data structure, and we can move forward. So in our agenda for today, what I told is we'll be doing these programs, and then I'll be introducing you to binary search tree. But what I understand is we are running short of time. I think we have ran out of time, so we will do this introduction of binary search tree, which is also one more kind of a tree, tomorrow. And then there is one more thing, which is like after we are done with binary search tree, then we have something like balanced binary search tree, then we have AVL tree, right? We'll be seeing these examples tomorrow and the day after tomorrow class. These are not too hard, guys. Again, the code will be so simple that I showed you, right? So we will try to dig deeper, slowly, step by step, and find and try to learn about the other tree structures as well, and make ourselves even more confident in writing the codes for this kind of a problems, right? So okay, so I'm trying to put an exam. Maybe we'll be having having a HackerRank exam. So I'll be telling the actual date. Maybe we'll plan that for the Saturday or Sunday. So what I want you guys is to actually practice what we have done till now. These are simple codes, right? These are simple codes. So I just want you to practice a lot, and finally you can be in a good position to take the exam, right? The reason for having this exam is not exactly to test you, are you doing good or bad, guys. It's not like that. It's like giving you a confidence that, after learning this theory or after learning this data structures and algorithms, so you will be in a position to actually write code in HackerRank kind of a platforms. And let's say you're given some exam by any big company. So if it is a HackerRank test before you appear for an interview, then that should give you an ample from starting or only trees. Lata, I don't know like until what point you have completed, but I'm planning to have an exam since start until here. I can do one thing like since you'll be having a question on trees as well, maybe I cannot expect 100% from you. Okay, but let's see. You can answer the exam. You can answer the exam with confidence. Let's see. Even if you doesn't, then that's fine because you have joined a little bit late. You joined the class a little bit late. There will be an excuse for you, but you know maybe I'm trying to give the exam with some simple questions, maybe the questions that we have done in the class, or maybe the questions which are having the similar pattern that have been in the class, right? So that you can write the exam with more confidence. Okay, no problem, Lata. Like maybe start preparing. Maybe we'll be having that by Sunday. Slowly, don't be in a hurry. Okay,